Damn it to hell. God. Grab my microphone and put it over here. It's actually a camera, but I just point it towards me a little more. Actually, that's right next to my bird, too. I don't know, this stupid camera's... everything's messed up here. I got some noise on here too, I don't know where it's coming from. I'm not gonna deal with it. It's some noise on the camera itself, the camera microphone. I have to come up with another mic setup or something. Anyway, I'm in the process of eating a meal, and I don't know why this thing is still sticky. Oh my god, the fork is all sticky. I'm having a wonderful meal. Oh my god, are you kidding me? I'm not having a good time right now. So I'm going to show you the circuit here. Get all this stuff put up here. Alright, so first we have image capture, and then we have the circuit somewhere here. So this is sort of the Raudive diode setup thing, but we're not going to do that. We're going to build hack. I can actually look at the stream, and because I get another monitor that has the diagram on it, but it's too far away to see. We could even put an inductor in here in place of that virtual setup. Oh God. Listen to that damn bird. Cut it out! Cut it! Cut it out! I don't know what the fuck is he doing? Quit it! No, stop it! Behave! I can't multitask today. Oh my freaking God! Cut it out! What's the matter with you, dumb bird? He is really annoying me. I don't know where. Why does this say variable? I don't know where the resistors are. I could just place a resistor and set this value, but oh God, I can't even find it in here. Why do they go from? Oh, I see what they did. R7. God, R9. R1 and R2, that's over here. I don't like what they did here. Why can't I just copy? There we go. Oops. Oh God, I hate this. Just messed up. Oh, yeah. Oh, everything's going on all whack here. Now I can't grab the whole thing. I don't know what's going on. Shouldn't take too long to build this thing. I've never even tried this either. The numbers are incorrect, but that's no matter. I don't care about that. Looks like there's a capacitor in there. I can change these values in a minute. Bear with me for a minute. I just actually, yeah, that's the web page. Something's gonna get blocked. I just have to look here. So they've got one op amp with 2 resistors on the input, and then they've got another one with a resistor and a capacitor on the input. This section on the left, or the section on the right, is the representative of the inductor. I think. No. Wait a minute. I think the one on the left is the representative of the inductor because it's got L on the top. That's the gyrator circuit. Okay, so the gyrator circuit's on the left. That can be replaced by an inductor of around 18 millihenries. The circuit on the right is is that the Choas circuit? No, the whole thing is the Choas circuit. But it's a modification. Well, never mind that stuff. This is a bridge circuit. There is a formula for the I mean, you can't see everything on the web page because it's a little messed up. Let me just skip through this. I just want to see what it says here. I want to measure across the capacitor. Oh, I was measuring across the resistor last night. I'm just trying to figure out. Good. I'm just trying to. I want to explain the circuitry in layman's terms. There is some formulas. You can't see everything on the web page just yet. Just bear with me for a second here. So the left side of the circuit In the middle, there's a resistor in the middle, and there's two capacitors on either side. So what that represents is basically a low-pass filter. There's also, it represents impedance matching. So the circuit on the left looks into an impedance on the right, and that impedance is a capacitor in parallel with a resistor capacitor combination, R and C1. That's in series. The circuit on the right, when it looks at the impedance on the left, it sees capacitor C1 in parallel with R and C2 in series. That's an impedance matching network. That's what that's called. There's some formulas there. I'm not going to get into the formulas. That's what the curve should look like. But it's not telling me something. Oops. Well, let me just get this back into the picture. What? Some of my YouTube stuff up in there. At any rate, the circuit on the right looks to me like that's like a Weinberg circuit. A Weinberg circuit is, or a whetstone bridge circuit, is a circuit that has 4 components, and when you measure between the components, there's what's called a null or a zero differential voltage. So if anything changes in one of the arms of the bridge, then the voltage in the middle, it's very sensitive, like it's on the order of microamps. So I can't remember, I don't know in the description what they're doing with this circuit on the right, but that's definitely 2 arms of a bridge circuit. Now, as I build this, let's put these op amps in there. I'll just put that one. Let's see, those are across from each other, so maybe here. Yeah, that one there, I guess. I move it a little bit closer. And let's add the resistors. Oops. Now, of course, them ones are going to be. Let's see. Let's put this one here, somewhere in here. Oh, my bird. I have to move this over. Hope you don't get. Look at this. Oh, I don't know why I have to grab everything in parts here. I need another resistor. Where's the resistor? Here? Let's see, we need one up top between plus and minus. Uh-oh. Alright, so those are the feedback loops. connect from here to here. And these guys are connected. Oops. And I can probably well, let's just do it this way. Wait, can I even do that? How do I connect them lines together? Do I do a wire? A line? Oh, I don't want that. That's That's just to cut that. I can go from component to wire, but I can't go from wire to wire. Let's do it this way. Let's see. Oops, my picture's not quite lined up. I'll have to fix that a little. No, that didn't line up there. We need a resistor and a capacitor in the middle. I'm going to do this other circuit. See, I've got that in there. I have the resistor and the capacitor is not connected yet. That's that. Now I've got to connect the output to the centers. That connects to ground. We need a ground point. Where's a ground point? Ground. What does it say to cut that wire? I don't know how to connect this wire. It's like I have to have another component in there. I could do it that way. Oh, that's cute. And then just connect the ground to that. What else is connected to ground? I got a resistor capacitor network in here. Uh-oh. Did you do that to me? Now we connect this resistor to here. We could do some simple simulation first, and I'll show you exactly what's going on with. Oh, I shouldn't have done that. Oh, I guess I can do this. Uh-oh, see, I cut that, didn't it? Alright, so let's see. We get the top part, that's plus minus. Just a second here. Oh, plus is on the bottom. On the other one. vertically. And let's reconnect. Alright, so that's connected. We've got a resistor here. We need to connect this node to ground. Oh. Oh, it worked. Oh, there's a node there. I can connect off of that node, maybe. I don't know. Anyway, that's all connected to ground. I know the wiring. See, now another thing is like the wiring. The way the wires are on this, it doesn't matter. But I don't believe that the simulator takes into account the length of the wires as far as capacitance or anything. This is more of an ideal type of a circuit thing. Now let's look at, see, that's connected, and that's plus minus, that's minus plus. That's connected, and we got a resistor there that goes to ground. That's connected to that center portion. And then that resistor connector goes over to here, which is not connected yet. And on the other side, we have two resistors across there. Let me just make sure that I have that orientation correct. I do. So there's a resistor there, There's a feedback loops. And then I got a resistor here. And a resistor there. And these two guys, and they're connected to ground. The only thing that's not connected is these two components. Alright, now let's put the values in. I'll just put the values in there. R8 is 1K. R9 is 1K. R10 is 2.5K variable potentiometer. 3K. Virtual linear potentiometer. I have unsuccessfully tried to use a potentiometer in this, and just does not work very well. Maybe we could just use two ends and see if that works. Wait, that's a R10 is a potentiometer to ground. Oh, wait a minute now. I thought R was a potentiometer. 2.5K pot. Uh-oh. It's putting the nodes back. So you know if I can paste that in here. And just leave that like it is. Display value. I wonder how you use that in the circuit simulator. Do you just go to it and change the values? I have no idea. C2 is a 10 nanofarad? No. What do we got here? C 100, 10, and 100. So C is 100 nanofarads. C2 is 100 nanofarads. That one's 10 nanofarads. Uh, 100 ohms, 1K, 1K. That's a resistor, we got that in there. Let's see. Those resistors are in, that's in. And then we've got R1, that's a 220. R2 is a 220. R4 and 5. That's a 2.2K and a 22K. K. Wait a minute. Something ain't right. R4 and R5 are 22Ks. I thought something was wrong there, because that would have made it unbalanced. Except for the fact that these other resistors in part of the bridge are different, that means it's going to be a current flow. R3 and R6. That says 2.2K, 3.3K. Let me just get back up in here. R3 2.2K, R6 is 3.3K. R3. I ought to make that a variable resistor. Let's do something here. Let's make this a 2.2K. And then what I'm going to do, let's cut that. Let's do this line from here to here. And then I'm going to add a variable resistor. Actually, let's make this, oh wait, yeah, let's leave it at 2.2. And so if I'm adding to get 3.3, we could make this we could make it a 2.5K resistor, couldn't we? I don't know how that works. Now we're going to save this. Let's save it as 201. We need supplies on we need the op amps. Oh god. Oh, I can't for some reason I have a problem with the types. It won't load the models. I built this whole well, that's okay. I mean, let's do this. Let's add we need to add a generator. And then we need to add an oscilloscope. Somewhere. I guess the whole display is in there. This is a 2-channel scope. We want to connect generator to there. What I'm doing is I'm hooking up the generator and wait a minute. What about the supply voltage? See, I don't think it'll load the models. can't access the database. It's some weird, stupid. I have to reinstall. I gotta do a bunch of stuff on my computer. It's messed up. The virtual op amp might work. Anyway, those are sitting there. That's tied to ground. Is there a ground on this? Trigger. There's a ground. Trigger, ground, and prompt compensation. Might be that middle one. Then I put the scope here. Put the generator over here. Let's see if this thing will simulate. Actually, I don't think I even need those on there just yet. So let's hit, wait, let's save it. And there should be a button, but let's just run it and see what happens here. It does seem to be running. Now maybe I can change the resistance on the fly here. Let's change it to 1.1K. And the other resistance, I don't know, it's at 1K. Alright, so what we're going to do, what we're looking at is we're going to just look at this transfer function impedance bridge here, and we're going to turn on this equipment. Somehow. I want a frequency of, well, I guess 1 kilohertz maybe. It's already at 1 kilohertz. Amplitude. How come I'm not getting a reading up here? X. Channel 1. And I don't know what that's doing. Where's my... There we go. There's channel 2. Let's see here. Y. Okay, both settings are, wait, just a minute. Okay, here we go. 100 millivolts. What the hell is going on here? They're not in the same position. It says 100 millivolts peak to peak. It says 200 millivolts, but it's in a different position on the scope. It keeps changing on me. Now it's way the hell down here. Well, that's a problem with the knob. Okay, we just go by what's on there. That's strange. The knobs are not lined up correctly. I wanted to move that trace down. I can't change the color on that. DC coupling. Anyway, they are identical. Let's go change this frequency here. Let's see. Okay, now we're actually getting a little bit of a phase shift, I think. Let's run a line. I don't know if I can do it now. I have to run a sync line. From the scope to the first trace. There's a sync output. And that needs to be connected to probably the trigger. Well, that's okay. Let's just keep going here. Alright, so what's happening? Let's make sure we know where channel 1 is. That's channel 1, the larger trace. The smaller trace is channel 2, meaning you've got a larger signal coming from left to right and a smaller signal going on at the output there as the frequency goes up. So what that means is on the output, the higher the frequency on the output is going to get shorted to ground by the I think that one was a 100 nanofarad capacitor. No, that's a 10 nanofarad. I mean, for all intents and purposes, see, now I'm thinking in terms of an audio filter. That's or either an audio filter or a filter such that if, let's say, if I'm picking up a signal that's within a certain range, and I want to get rid of the, I have to get rid of the noise. Wait a minute. I'm not. There's two possibilities. Number one, I'm getting rid of the noise with this filter at whatever frequency I'm trying to get the information from, or I'm using the filter. Yeah, it sounds like better. Like I'm using the filter to extract the information from the noise. Or that's not accurate. I'm using the filter to resonate with the frequencies that are being generated in the noise, and that's similar to the idea of what's called stochastic resonance, where you add noise to information in order to amplify that information. What happens is the noise is all the information, or rather the information plus noise or whatever, and then that noise will give some strength to a weak signal, and it will resonate with that signal. And then you have to do some phase shifting and such to get rid of the noise. You combine the two signals. You combine the signal and the noise with the noise. Then you phase shift the noise to get rid of the noise from both, and all you have left is the signal. And so what we're doing here is we're finding the limit of where the noise cuts off. Actually, in this particular circuit, the frequency is getting shorted as we go out on the right hand side of the circuit. So let's keep going here, and you can see how that's getting smaller and smaller, sort of. Yes, the input does not seem to be affected too much. Now, there's also what's called, and there's I think there's a phase shift. Ooh, there's a major phase shift. That's almost like 45 degrees, I think. That's about a 45-degree phase shift. And that I'm not 100% sure about the phase shift, because it could be that the scope's not triggered correctly, and I might actually set that up and see what's happening. There's also what's called the 3 dB drop, which has to do with your filter characteristics, and we might be able to see that. Well, we'll just keep going. Let's do let's see. Let's go back this way. Let's see here. Now maybe we're going to crank this thing. Oops. I went too fast for the scope to catch up or something. So here you can see if I'm trying to extract information from a 200 kilohertz signal, say somewhere in that circuit, whether it's on the right or the left or wherever, I'm going to lose some information there. And so let's go back to anything above 200 kilohertz, and I'm going to lose information. The input seems to be fine. Let's turn this, let's look at, just out of curiosity, let's see here, wait a minute. Let me back this off again. See, we'll use 50 kilohertz here. Well, I needed to add another. We have to shut this off. Somehow. There's a sink on the generator, which is the top thing here, and there's a trigger on the scope. Oh, I got the ground line connected. You can see the little dot there. That's cool. It's a little dot on the scope. That's pretty neat. All right, so let's connect the trigger output to the sink on the generator. And what that does is synchronizes the pulse to the trigger, so that then when you look at the scope, there's a trigger function, and here's the level of the triggering. It's edge triggered, and what that will do is it will trigger on. Yeah, it'll trigger on the frequency. No, wait. It should trigger on, like, channel 1. It should trigger on channel 1. That's usually the way it's set up. If you've got both of them on. Channel select. That's a digital thing here. Mind control. I think so. I think that's what that means. So that part of the circuit, so we've got that figured out. It's running anywhere from 0 to 200 kilohertz. I thought that there was another circuit they were running up into the megahertz range on this attractor type noise setup. Let's add another component in here. There's a spectrum analyzer. Input and trigger. Well, let's connect the trigger to here, and the input is going to be over here. So we're inputting the signal from left to right, and we're looking at, oh wait a minute, that's not, yeah, that's correct. Wait a minute, that's not right. Wait, yeah, I guess it is. Okay. Oh, that's strange. Oh, wait just a minute, something's different here. Wait, so the signal goes in to the resistor, and it comes out from the resistor, because that's what's connected, that's what's going to be connected to the circuit. Yeah, okay. Let's run it again. So we've got 50 kilohertz going on. Is this working? It's just slow to catch up. I want to look at 100 kilohertz. Now it looks like it's still a phase shift there. There's something else we gotta do too that I haven't done. I almost forgot about it. Oh. Why am I not seeing anything? Span is 100 kilohertz. Why is it so low? Never used that spectrum analyzer, I guess. Wait just a minute. Wait just a minute, I got another idea. What we can do here. There's nothing coming on. Oh, you know what? We're getting there. That spectrum analyzer connection was messing things up a little. I think on this generator, I don't know if I can do a sweep. a square wave in there. It's a little bit slow. Where's the function? Oh, here it is. We're in sweep mode. Sine wave. I don't know. I'm not sure what's going on here. I wonder if the levels are too low. What did I just do? Amplitude. I'm not sure how to use the sweep mode on this thing. I don't know what it's doing here. It's really acting weird. This is just a filter. Alright, I'll tell you what, let's just drop this. I mean, we get the general idea of what this thing is doing as far as the filtering goes. So let's go ahead and let's cut this out, and we'll connect these wires. We got channel 1 and channel 2. That's where we're supposed to measure. We can put that to an XY. And all we have to do is connect that node to here. And then we've got to connect this node. My bright goes, to there. Now let's see what happens. Nothing. I'm not surprised. Let's leave the scope up here. Well, that's 3.3K. Supposedly. According to this, nothing's happening. I don't know. It could be the fact that it's an ideal circuit. Wait a minute, what is this value? $1K. Let's make this I don't think it's gonna make any difference. Oh, wait just a minute. Oh, wait just a minute. Hold on, hold the horses. I made an assumption that there was power connected to these op amps. Strange. Let's use, let's put a supply in here. I'm assuming positive is to the positive is positive, negative is negative. I made a bold assumption there. My bird's laughing. Ow! Go ahead, laugh it up, fuzzball. Flip vertical. I want to change this to 9 volts. And the minuses, wait, something's not right. The minuses, the minus on one is connected to the plus on the other, so that we've got plus 9 volts on one side and minus 9 volts on the other. So the plus is going to be connected to the plus, and I will connect all the pluses up here. Sorry about that little bit of inattention on my part. I was wondering kind of why it didn't make any sense to have something, you know what I mean? So that's minus, this is minus. Alright, now we've got our op amps connected. Oh, wait just a minute. I did something wrong. I did something wrong, didn't I? Oh, no, I didn't. That's plus, and that's minus. That's the only one that's flipped. Okay, let's save this again. And let's fire it up. And wouldn't you believe there's still nothing there? There should be something there. Maybe the scope's loading it down. I have no idea. let's try something else here. Let's put in a meter. That would be the two. Wait a minute, this is ground? No. It's going to be the two short ones. So I want to measure from here to ground. It's reading 16 volts. Why am I getting 16 volts from there to ground? Oh, well, I don't know. Let's measure across the supply and see what that says. $18 volts. Well, that's the circuit, but it's not working. Let's try something else. Let's get rid of these variable resistors here. Let's change this to a 3.3. See, what I'm thinking is I can't control these other two variable resistors. (22, 22, 202, 202). Output's connected to those two guys. Output's connected to those two guys. Those two guys are connected. That's ground. I got two variable resistors here. That one's set to 2.5K. And this is an inductor. Let's try something else. I'm going to save this. And what we're going to do crap. That resistor stays in there. My plus supplies are connected. Minus supplies are connected. This is connected here. That's to the scope. I need to connect from there to here. How do I get rid of this node? going to put an inductor in here. $14 millihenries. Now let's start it. Let's save this. Whoa. Oh, that's interesting. Something's happened. Something has happened. Let's stop this. So what's happened is this circuit on the right did what's called a startup. So when you have a chaotic circuit, or when you have an attractor, I should do like a mathematical thing about this. That gets into a little bit more detail as to how these attractors work. So what it is, it starts up and it goes through what's called iterations. The first 1,000 to 5,000 iterations means it's at this the math of the thing is trying to figure out what's going to happen. Is it going to be a pattern like a sine wave? Is it just going to bounce back and forth? Is it going to be a complicated pattern where it hits half a dozen trajectories and then it repeats itself? So there's a point where it's like a number that just keeps repeating, like an irrational number or something, and then at some point it repeats itself. Now that repetition is not chaotic. It would be chaotic if it never repeated itself. However, the points that get generated are attracted. They're enclosed in a certain space, and it looked to me like it was doing a startup. But the voltage level that we had on here, obviously, it wasn't. I mean, I don't know. We could set the voltage level a little bit. It went to a high voltage level. I wonder if we can start it up with that scope sitting there. There's the other part of the circuit. They're rising and then they're going up to the top. That's cute. So the first capacitor was charging up. Then the second capacitor started charging. And it's probably gone to the 9-volt rail. Ooh. Oh, what's going on? The second capacitor is doing something strange. Look at this. It's doing some weird shit in there. I've got to look. This is just a, oh, see, this is a bridge circuit, and it's something to do with that inductor. The way the inductor charges and discharges through the circuit, and I don't know what this is doing. I don't know if this is part of the iterations. It could be doing some complex math in the program, and that's why it's taking so long. When you have an electric circuit, it doesn't do the math, it does whatever it's supposed to do. I like how the scope automatically sets itself. I wonder if that second capacitor is discharging. Yeah, but that's a very high capacitor. I mean a low value capacitor should discharge like nothing. I wonder if that the circuit that simulates an inductor, what the heck is it called again? Gyrator. I think the gyrator circuit's too active. It doesn't represent, I mean, see, an inductor has peculiar characteristics. I would think this gyrator could not possibly emulate or simulate an inductor properly. Jeez, I gotta go for a ride for 2-3 freaking hours tonight, I think. Why is the voltage on that? Wait, that's channel 1? This is channel 2. This is channel 1. Channel 1's on the bottom. Yeah, why are the voltage levels so high? That's 25 volts. Oh, I know why. I know why they're so high. It's because those op amps are acting like an amplifier with a very high gain. How is that RC network connected to? See, that's an RLC network now. Oh, minus is connected to ground, isn't it? We should set this up as a bridge circuit and see what it looks like. So I can see I can see two legs of the bridge. That's connected to ground. The inductor resistor is connected from there to ground. Something's not right with this circuit. It just doesn't seem right. It's not the way the circuit was built. I'm going to set this up as a bridge circuit. We're going to see what it looks like. Maybe we can do it while this thing is just doing what it's doing. I don't know. It just seems to be decreasing over a long period of time. Let me stop this. Let's do just throw this inside of my window. So what we've got, let's do the amplifier sections in red. Shit, I don't have my... There's the two amplifiers. We've got let's use the orange capacitor for the input. Let's use the yellow for the output. Looks crooked. And we use green for the resistor. We use brown for the inductor. Let's make it look like this. That's the inductor. And we use blue to connect everything. Now, if I look at the circuit itself, I see a complete impedance across. I see an RLC network across that bridge, but that's not what we're looking at. There has to be a bridge circuit in there. Just trying to figure out where it is. So if I do, let's say if I do a bridge circuit. Then we have, let's say we have this guy. Wait, let's see if we have this guy as part of the bridge. That would be, let's see, that would be down on the bottom. And that's connected in parallel. It's connected across each other. If that's ground, wait a minute. And oh wait just a minute. There's nothing. Let's see, that's the amplifier. That's a resistor. That's a node. Let's see something. Let me try something here. Let's grab select. Let's grab this guy here. We'll put this one here like that, and then grab this one, put this one here, and then a resistor here. This is on the, this is just on that other circuit on the right. This doesn't include the other components. There's an amplification of 1. Wait a minute. Yeah, I think it's an amplification of, I don't know what that is, what kind of a circuit that is, that op-amp circuit. Let me just draw this here. Let's see, let's do this. Let's get, let's see, red. So like this op-amp circuit looks like this. Oh crap. This is plus, this is minus, and there's a resistor. And they're the same values. So they both have a value of X. I think that's a bridge circuit. The whole circuit on the right is a bridge circuit. Except, like, one side over here would be 220 ohms, the other side is 22K, I think. R2 and, let's see, R1 and R2 are 220, R4 and R5 are 22K, and the only difference that resistor goes from minus to ground. Is that what that looks like? Let's see here. Minus to ground. Okay. This resistor is 2K. Let's see here. This is 2K. And this is 3K. So the bridge is unbalanced. This is the op amp on each one of these. It's like, that's the op amp. And the output, well, actually, that's plus. Oh, it's the plus side on each of those op amps is tied together. So we could call this plus, I guess. This is plus. And the minus is tied to those resistors. I think they were saying these are negative resistances. That's what this circuit is. Now I remember. This is creating a negative resistance circuit. But it's unbalanced. Maybe that's why they put a potentiometer in here. R6? R10 is a variable pot. Oh, I was going to put a potentiometer in there. In other words, I wanted to have this set so that this would be 0 first. If I turn the op amps on, there's nothing, they're just going to sit there. There's no signal going through them. But once a signal, somehow a signal is going to get generated. There's no signal generation. How's it going to start up? Yeah, something's not right. But that's what this circuit is on the right. It's a negative resistor. So if I look up, if I go to my web page here, let's see. How do I do that? It's supposed to be the whole web page. Something's not right because it's not displaying correctly. Oh, it's stuck over here. Now see, there's different kinds of negative resistor op-amp settings that you can create. You can add a capacitor in there instead of a resistor. There's different types. Negative impedance converter. What am I missing? Why did they have... X and Y. What's P? X is across C1, Y is the voltage across C2, and Z is the current through the inductor. They can measure the voltage at point P. 0.1 volt per division. That's in the hundreds of millivolts. See, it goes into synchronization of two circuits, which is, one is a master circuit, one is a slave. I haven't even got the first circuit to work yet. Another thing too, in the circuit itself, the wiring is very short. All the leads are very short. Whereas in mine, I've cut them all over the place. They're kind of exposed. I don't want to cut the leads on my components. I mean, they're going everywhere. Oh, I can see these two resistors. How the heck did they get them in there like that? There's 3 resistors over there. They just connected right across that, and then they've got wires connected to the op amp. Honestly, I don't know. I just don't know. Let me go back to this circuit. So that forms a bridge. I should have my circuit in there so we can have something to compare to. Let's see if I can put this thing on here. I gotta jumble a few things around on my web page. Alright, let's try this again here. So there's a bridge circuit. These are negative impedance resistance circuits. You know what I gotta do? You're probably gonna get mad at me here. Let's see if I can just Things are going to get a little discombobulated here, but I may be able to just stick this in here somehow. Wait, let me go back to Wiki. Let's see what that says in here. See, here they've got a signal source. Non-inverting amp. The op amp and the voltage divider in the figure of the resistor R3 connected between its output, etc. Non-inverting. That's the plus side. Oh, this is creating a current generator between IS and RS. The combination of the real generator and the INIC will now behave like a composed real ideal current source. An example for a current source is shown on the figure on the right. The current generator and the resistor within the dotted line is the Norton representation of a circuit, comprising of a real generator and RS, its internal resistance. If an INIC, what do they mean by that? An NIC is a negative resistor. Non-inverting. I don't know what they mean by that. Negative impedance converter is a one-port op-amp circuit acting as a negative load which injects energy into circuits in contrast to an ordinary load that consumes energy from them. This is achieved by adding or subtracting excessive varying voltage in series to the voltage drop across an equivalent positive impedance. This reverses the voltage polarity or the current direction of the port and introduces a phase shift between the voltage and the current for any signal generator. The two versions obtained are accordingly a negative impedance converter with voltage conversion, VNIC, and a negative impedance converter with current inversion, INIC. Negative impedance converter. Okay. The application behavior in this, the ideal behavior in this application depends on the Norton resistance RS and the INIC resistance being matched perfectly. As long as our INIC is greater than RS, the equivalent resistance of the combination will be greater than RS, etc., etc., etc. However, if 1 over R INIC is greater than the sum of 1 over RS plus 1 over RL, this circuit is unstable. In particular, surplus current from the INIC generates positive feedback that causes the voltage driving the load to reach its power supply limits. I think we observed that. By reducing the impedance of the load, the generator system can be rendered stable again. Well, there's 3 different types. I mean, it sounds to me like there's a current being generated. It's a very small current, and then it gets amplified. And they've got 2 of them in parallel. That's one part of the bridge. In other words, that's a voltage input. There is no voltage input though. Now after manipulating these equations using a moderate amount of algebra and letting R1 equal R2 for simplicity, R1 equal R2, which they've done in that circuit. They're not exact, well, they're exact in this circuit. Vn is minus I1 times R3. I1 equals V, the difference between Vn and VOG. I'm not sure exactly what VOG is. Because we established our input voltage as positive and our current I1 is positive when going down from Vin to ground. We know that there is a negative current going from Vin to ground so long as R3 is a positive resistor. This implies that the direction of the current is actually going from ground to the voltage input. You can hook up a positive voltage to the terminals of our circuit and an ammeter in series with that circuit, and you will see a negative number on the ammeter. It takes a power supply to run the converter device, etc. Inside is an amplifier that takes energy from external power. But the device we have created has some very interesting properties due to its tendency to force current to go the wrong way. This means the NRC pulls power to the circuit or energy rather than dissipating it like a resistor, i.e. negative resistance. What do we use it for? They're taking these negative impedance resistors and they're, I don't know what they're doing on the left with this Choas diode circuit. Negative impedance converter. They show a voltage going in, but what's happening, there's a current going from ground to VN. There's a current going from ground to VN. So then what happens is this circuit starts up. It's on the left over here. It goes from ground up to VN, which is the positive. And that current, that's a current generator. I wonder if I could measure that. I wonder if I could measure that current as a voltage. That's what's starting. That's just weird. What's this picture here? See, they've got a voltage there. Reinventing negative impedance. But this is the familiar op-amp current to voltage converter. I don't think we even ever studied this way back in the day. I mean, we were into op-amps back in the 70s, and I think this even existed back then. I mean, this is quite a conversation here. Ordinary positive resistor. Okay, you've got a voltage, and you've got current flow from plus to minus. With the negative resistance, you've got a helping negative resistor. So what it's doing, it's actually adding a current. L is a load. Let's say a current I passes through a positive resistor R into a negative resistor minus R. As a result, only the resistor R sucks a voltage VR equals R times I from the circuit if it is a voltage drop, while a negative resistor minus R adds a voltage into the circuit. So the resistor acts as a current to voltage drop converter, while a negative resistor acts as a current to voltage converter. While a negative resistor is actually a voltage source whose voltage is proportional to the current passing through it. So there's a current being generated. NIC is just an additional voltage source which produces a voltage proportional to the current passing through the source. This voltage is added to the input voltage. Okay. Well, if that's the case, why not just take the basic circuit? Just take one of them, add a resistor, and see what the current flow is. Let's see what happens here. I'm getting into this too much, aren't I? So if I've got, let's see, I've got this, and I have a resistor. Here. Now we put a line from there to there. Need a battery. I use 12 volts. Get this guy here. That's from negative to ground. Yeah. Now we're going to need I want to see what it looks like though. So if I measure from the plus side here, here, this is ground, this is ground, and we change this to I don't know. Let me see that. Let me see that R1 and R2. If RNIC is greater than that, this circuit is unstable. 1 over RS plus 1 over RL. 1 over RL is a load. If the load is very high, if it's a very high resistance value, that number is going to be low. Do we have to have a load? Wait a minute, there is a load. It's being fed back into here. Let's put that in there. Let's see what happens when we fire this up here. I think I can actually turn this on. I can have this stuff turned on. So now we've got our basic circuit, a basic negative impedance resistor. Just one portion of that leg. And what we're wanting to do is we're wanting to see the current that's developed. We'd have to have a resistor though. Hey, wait just a minute. You're right. No, wait just a second. let's do a resistor. Let's call this 1 megohm. Actually, let's do a 10 megohm resistor. Now let's make it 1. And we will connect that from positive to ground. I don't like the idea of connecting it to ground for some reason. Don't ask me why. So what we're looking at is a voltage developed across this resistor, 1 megohm. If there's a if there's a current going from from ground to plus, no, something's not right. Something's still not right. This can't be right. Something's not right. What if I put a resistor across that terminal? What if I just measure I need to measure current. That's just not gonna work. That's not right. Something's not right. Let's do this again. I'm gonna get this figured out. Okay, wait a minute here. Let's delete this. What about this? What about something's missing? Something's okay. Let me get rid of this line. Just get this confusion going here. What about the voltage across just a minute? Let's make this a lower value. Let's watch the voltage across the 2K resistor. My ground wire doesn't want to. Alright, so we're going to watch the voltage across this bottom 2K resistor here. I'm going to fire up all this equipment here. And that's going to be a DC voltage. And that's turned on. There's nothing there. Let's turn this on. I think, wait just a minute. Do I have, I got plus and minus, okay. Turn this on. Something's not right. Oh, what's going on? This is a simple circuit. Did I even save it? I don't think I saved it. Something's wrong. It's froze. Oh. Alright, let's save this. Save as negative resistor 1. Negative resistor A amp 1. Let's start this up again. Why is it taking so long to start? That's a negative. That's a negative. What the hell is going on here? That's reading a negative 0.1 volts. Why can't I see it on here though? It's not connected. I must have connected the trigger. I connected the trigger. What if I can do this live? Oh, I can? I just lost the voltage. I don't think I can do it live. Something happened. I wonder if that scope's loading it down. Let me get rid of this line. That's interesting. That's a negative voltage drop in reference to ground. It's creating a current. That's in the negative. Wait, that's microvolts though. What the f is going on? Why doesn't the scope see that? That's 0.1 millivolts. That's 100 microvolts. That's a very small current. 100 microvolts. Wait a minute, no, it's 100 microvolts. 100 microvolts over 2K resistance. So what's going to happen? Alright, so now I understand. Alright, so from the positive output on that circuit, you've got two. First of all, you got two of these connected together. This is going to form a bridge circuit, and these are two arms of the bridge. Okay. the voltage we're measuring across that 2K, if you look back into onto this circuit here, is this, we'll say it's this 3K resistor on the bottom right hand corner. So in the bottom part down here will represent ground. That's ground. Now, so what we have is we have two of these connected in parallel. This forms a bridge, and we've got a current going in this direction. That would be represented by orange, I guess. That's not orange. Well, because I don't know what the heck's going on here. Where's my orange? Orange. And in this case, we've got a 2K resistor. It's similar to bridge. Well, I don't have the parts listing on there. Let me see if I can get the parts listing up. This will be a little bit discombobulated here for a minute. Just bear with me. We should get this settled up here in a minute here somehow. How do I get that over there? I'm not feeling too good today. I had a rough night last night. Oh, this is supposed to be on top. Well, it isn't. I don't know, that's as good as I can do it. I just deal with it, I guess. Oh, God. So theoretically, if we have the other side of the bridge is producing the same amount of current, some current's going to go the other direction if it's not the same or something. I don't know, it's weird. But I can see a voltage there. Let's shut this off. Let's change these values to 220 ohms. Wait. Yeah, let's do that. So remember that we've got 98.0989 millivolts DC minus. I want to see what the current is. Oh God. See, we're getting into a little bit more of the nitty-gritty into this because I want to understand. I want to know the intricacies. I could be getting into this a little bit more than necessary, but if I don't understand the basics of each part of the circuit, then I'm not going to be able to understand how the chaotic patterns developed in the first place. So I'm understanding what's going on here. So this is acting like a current generator. According to this, it's a very small current. There's a negative voltage across this, which tells me there's current going from ground to plus, I'm assuming. If it goes the other way, if current goes from the minus node to ground, you're going to read a positive voltage on that pin, because that's how current flows. But there's a current going from ground upwards. It's a very small current, granted, but that's all that's needed. but it's a DC current. It's a DC, and that DC will do something to that RLC network. It may charge up that capacitor, and then the inductor that's in parallel with that, it will act as like a bandpass filter. It will start to resonate is what's going to happen. There'll be a point of resonance. And then they've got variable resistors. They've got a variable resistor on the other side of the circuit, which is simulating the inductor. And they've got another resistor that connects the two together. That's a variable resistor. So there is a variable resistor in the RC network, RLC network. And that's used to the current going through that is going to charge, and the capacitor and the inductor is going to discharge it, and it's going to keep going back and forth, back and forth, back and forth. And it may also even send, that's going to develop a voltage drop. And it's going to increase and increase and increase. How did they ever come up with this idea? It's just, I mean, you could create a voltage. It seems like you could generate, this is just a bridge circuit. That's all this is. It's a very extremely sensitive bridge circuit, and it's got an op amp in here, which is prone to oscillation and whatever. It's got cutoffs, and it's got its own set of parameters in here. It's a feedback loop, and it's an amplifier. And what happens is it's going to, the RLC network is going to interact with this, and it's just talking too much. 220 ohm. Did I do this right? Oh, God. I'm going to have to take a break here in a minute. Let's see what this voltage is. I'm hoping it's the same amount of voltage. That's what I'm hoping. But it might not be. We'll find out soon enough here when it gets started. I don't know why it takes so long to get started. It must be going through a number of calculations. Ah, that's developing a quite large positive voltage across that 2K resistor. Uh-oh. Why can't I get... Oh, the scope is up. What's going on here? Did it short out? 0 volts. No voltage drop. Why? Let's get this scope up here and maybe set this to, we had 300 millivolts, let's see, 500 millivolts. Let's start it up again. Maybe we can see it on the scope. Oh, look what happened. Why did it do that? Well, what's going on there? Does that resistor have to be... Why did it do what it's doing? 220 ohms. That's what they got in that circuit, I think. R1 and R2 is 220 ohms. R3 is 2.2K. And R4 and R5 was 22K. That's a big difference. Well, let's run it again. This time we got the scope here. So for some reason it's saturating. Something's saturating. It says the voltage is going up. That means it's becoming open. It's developing an open circuit. I wonder if that's by design of the... if it's developing an open circuit. So what would happen if we put them in parallel then? See, we're slowly building this Choas circuit up from scratch here, like part by part. First the bridge, or first half of the bridge, then the whole bridge, then the RLC network. See, it just goes up really quick. Let's try something else. Let's try 220 ohm, 300 millivolts. If I want a smaller voltage, let's change this to 200 ohms. I'm wondering if that's even enough. I'm not even sure what I'm doing. If it's by design and the voltage goes from 0 to an open, but that happens a lot slower, maybe we can get more control of the circuit. How did they ever come up? I mean, they've got two of these in parallel. Well, I mean, why would they would come up with the idea, I mean, you could just create a feedback loop and put it into instability. You can do that with regular transistors, which is another aspect of this whole thing that I'm doing, is that once we build something like this, we can't have op amps in the circuit at all. Okay, that's half the voltage. Wow, it just jumped right up there. It still jumped right up there to open. I think that's open. There's 0 volts. There's no current flowing there. Let's save this. And what we're going to do is we're going to try to add this other group in parallel. Oh, wait a minute. Let me see something else. Let's open... take this line. Why can't I delete this? What the hell is going on? I can't delete my lines. What the frig? Oh, what? It was being simulated. Don't ask me why. Okay, I want to delete that. That's my power supply. That's a. What is this? Let's delete this. $220. This is 3.3. I want to change this back to 2K so we can, because we know that worked. This is 220, and we'll make this 200. 220. That's there. None of this is connected. That's connected there. I want to disconnect the ground. Now I'm going to add another ground. I just want to be isolated from the other circuit. Alright, that looks isolated. This is ground here. And that's a 2-channel scope with both channels connected. That figures. Disconnected here. Channel B will connect to that node. Channel A connect to that node. Now we're looking at the voltage levels on both of these as they're both connected side by side in a bridge which is totally unbalanced because these two bottom resistors are different. I mean, there's a major imbalance here. And what I want to do is I want to see if I can create this bridge circuit and balance it out to have something that's, I don't know what I want really. I mean, it's got to be close to this Choas circuit design, but I want to figure out this circuit by itself and see exactly what's going on here. So here we've got that circuit. That's just the bridge part there on the right. Let's just start this baby up and see what happens here. So you can see there was a startup. But I can't. Let's start it up again. That's channel 1. Channel 1 was the one that had the change. Where's channel 1? Uh-oh. Okay. Damn. That, what the... Is that... yeah, that's... Oh, God, I don't know. Let me add a meter. There's a meter. I've got the meter on the right hand side connected. DC volts. Let's start it up again. I want to see what the startup voltage is. 350 millivolts. Oh, they both went up that time. Let's look at the other side. I wonder if the meter is causing an issue. See, that's another thing. In the actual Choas circuit there, they're suggesting to put a 1 megohm in series with your test measurement leads to avoid loading the circuit. That's 149. They didn't do that the first time, though. They're both going open. I'm trying to see if there's an effect on this meter. See, this is what you have to do. Sometimes when you do circuits and stuff, you got to go through process of elimination really slowly to figure out what's going on. They're both doing the same thing. They're both going open. The voltage on the right was 300 millivolts. The one on the left was 200. Wait, that's a 200 ohm. Let's change it to 2K, similar to the Choas circuit example, and let's see what happens. I want to separate them two circuits again. Nothing's happening. Right. What did I do wrong? What's wrong now? Oh, I changed it to 2K. That is a very... no. Actually, there was no variable resistor in that circuit. Oh, that's strange. One of them jumped up Oh, look at that. Oh, it's going down the negative. One channel is. Let's see how long that lasts. Oh, look at that. It went back up to positive. But it's not at 0. That's strange. And it's slowly going up to 0 to open. This is more or less an ideal circuit. One of them is set to 0 though. Channel 2. Channel 2 goes... Wait a minute, look what happens at the beginning. There's a voltage spike at the very beginning. I don't know which channel is doing it. Now I'm just looking at channel 2. Channel 2 is just staying at 0 volts. Now let's look at channel 1. Alright, channel 1, there's a voltage spike. And then it goes right to 0. And then it drops. But the other one's not doing that. Channel 2 is not doing that. Channel 2 is the inside. Channel 2 is the one on the right. Before it was acting the other way around. I'm going to delete the connection between the two op amps and look at these individually. I think I can do that. Oh, I needed to connect. Yeah, I'm going to have to stop the stream and come back.